Imagine holding the power of 1,000 suns in your hand. Seriously, not a metaphor, but a real physical thing. What if I told you a substance exists that's so potent, a tiny speck smaller than a grain of sand could unleash more energy than the biggest bomb ever set off? And what if this same stuff, the universe's most concentrated energy source, isn't just sci-fi fantasy but something scientists are intensely researching right now? A substance that could take us to the stars and, at the same time, offer cures for diseases that have stumped us for centuries. This isn't a dream. This is the world of antimatter, and scientists are right on the edge of figuring out how to use its almost unbelievable power. The question isn't if we can tap into this force anymore, but how soon and what will we do when we finally unlock it. So, to get a grip on this wild potential, we need to take a little trip into the heart of matter, or rather, its mysterious twin, antimatter. You know matter. It's everything around us. The air we breathe, the ground we walk on, the stars twinkling up there. It's made of tiny bits like electrons, protons, and neutrons. Well, antimatter is basically its mirror image. It's made of antiparticles which have the same mass as their matter counterparts, but the opposite quantum properties like electrical charge. So an anti-electron, which we call a positron, has the same mass as an electron but a positive charge. An antiproton? Same mass as a proton, but a negative charge. Simple, right? The idea of antimatter wasn't just a lucky guess. It was first predicted, purely from theory, by the brilliant British physicist Paul Dirac back in 1928. Dirac was tinkering with an equation that beautifully merged quantum theory and Einstein's special relativity to explain how electrons behave when they're zipping along at high speeds. His equation, which is a big deal in modern physics, gave two possible answers. Kind of like how x squared equals 4 can mean x is plus 2 or minus 2. One answer described the electron, but the other hinted at a particle with the same mass but an opposite charge, an anti-electron. This was a pretty mind-bending idea for the time, but it didn't stay theoretical for long. In 1932, an American physicist named Carl Anderson was studying cosmic rays and actually found the positron, the anti-electron Dirac had predicted. That discovery even earned him a Nobel Prize. Then in the 1950s, antiprotons and antineutrons were also found, making antimatter a solid reality. Now here's where it gets really energetic. When a particle of matter meets its antiparticle, they don't just nudge each other, they annihilate. This isn't like a chemical reaction or even a typical nuclear reaction. It's a complete conversion of their mass into pure energy, just like Einstein's famous E = mc2 equation says. And because c squared, the speed of light squared, is a ridiculously huge number, even a tiny bit of mass turning into energy means a massive energy release. This annihilation is the most energetic thing we know of in science. It's over 250 times more powerful than nuclear fusion, and thousands, even billions of times more powerful than burning stuff like rocket fuel. Think about it. Just 1 gram of antimatter annihilating with 1 gram of matter could unleash energy equal to several nuclear bombs, or enough to keep 10,000 100-watt light bulbs glowing for a whole year. That's the incredible power scientists are trying to figure out how to control. Trying to bottle up a power source this huge is, as you can probably guess, not easy. You can't just dig antimatter out of the ground or find it lying around. Nature does make tiny amounts during high-energy events, like when cosmic rays hit our atmosphere or in certain types of radioactive decay, but for any practical use, we have to make it ourselves. The main way scientists cook up antimatter today is in enormous facilities called particle accelerators, like the ones at CERN, the European Organization for Nuclear Research. These incredible machines, such as the Large Hadron Collider or the Antiproton Decelerator, get particles like protons moving at nearly the speed of light and then smash them into a target. The sheer energy from these collisions can create a whole shower of new particles, including, if we're lucky, antiparticle pairs. For instance, an antiproton might pop into existence along with a proton. These antiparticles then have to be carefully sorted out and collected. Machines like linear accelerators, cyclotrons, and synchrotrons are absolutely vital for this work. But the process is incredibly inefficient and, as a result, unbelievably expensive. Current estimates: producing just 1 gram of antimatter could cost tens of trillions of dollars. Some numbers go as high as $62.5 trillion per gram. To give you some scale, NASA's entire annual budget is pocket change compared to the cost of a teaspoon of this stuff. The world's current production rate is measured in tiny nanograms, billionths of a gram, per year. For example, CERN's antiproton decelerator makes about 10 nanograms of antiprotons annually. And creating a single gram would take an enormous amount of energy, roughly 25 million kilowatt-hours, enough to power a small city for a year. Once you've made it, storing antimatter is another massive headache. Because it annihilates on contact with ordinary matter, you can't just put it in a regular container. The container itself, being made of matter, would instantly go poof. So scientists have come up with clever devices called penning traps. These use powerful magnetic and electric fields to suspend charged antiparticles, like antiprotons or positrons, in an ultra-high vacuum, keeping them from touching the trap's walls. Some experiments at CERN, like the BASE experiment, have actually managed to store antiprotons for over a year, which is pretty amazing. Still, even with these advanced tricks, today's tech can only store tiny amounts for limited times, and the systems are complex and huge. The longest scientists have held on to antihydrogen, an atom made of an antiproton and a positron, is for about 16 minutes, and that was just a handful of atoms. Despite these massive hurdles, the sheer energy density of antimatter keeps scientists pushing. That E=mc2 equation means matter-antimatter annihilation is 100% efficient at converting mass to energy. This makes it the ultimate fuel. We're talking milligrams, thousandths of a gram, being enough for missions that are pure science fiction right now, like sending probes to the very edge of our solar system and even beyond. It's this incredible potential that keeps the quest for antimatter tech going, putting us maybe on the verge of a new era. Recent breakthroughs are helping too, like when the Aegis collaboration at CERN successfully used lasers to cool positronium in 2024. This helps us study antimatter with way more precision. Plus, Riken-led research has developed new systems for quickly cooling trapped antiprotons, which really speeds up research. The dream of traveling between stars, reaching other suns, and maybe even other worlds has fascinated us for ages. But the universe is just so incredibly big, it's a nearly impossible barrier. Our fastest spacecraft right now, like Voyager 1, would take tens of thousands of years to reach even the closest star system, Proxima Centauri, which is about 4.24 light-years away. The rockets we use today, based on chemical propulsion, haven't really changed their basic principles since the 1920s. They're just not powerful enough for the mind-boggling distances of interstellar space. This is where antimatter propulsion could completely change the game for space exploration. Why is antimatter so tempting for space travel? Its energy density is off the charts. When antimatter annihilates with matter, it releases way more energy per unit of mass than any other propulsion method we know. This means spacecraft wouldn't need to lug around massive amounts of fuel. That drastically cuts down their mass and lets them reach much higher speeds. Some studies even suggest that antimatter-powered spacecraft could hit speeds up to 70% or even 72% of the speed of light. Scientists are kicking around a few ideas for antimatter engines. One is antimatter-initiated microfusion, AM. This would use a tiny bit of antiprotons to kickstart a powerful fusion reaction in a small pellet of fuel, like deuterium and helium-3. The superheated plasma that results would then be shot out of a nozzle to create thrust. It's pretty amazing. A mission using just 5.7 milligrams of antiprotons with this tech could theoretically send a 100-kilogram payload to the Oort cloud, that distant icy shell way out in our solar system, around 10,000 astronomical units away, in about 50 years. Another concept is the antimatter-driven sail. Here, antiprotons would be aimed at a large, thin sail, coated with a layer of uranium. When the antiprotons hit the uranium and annihilate, it would cause fission, and the fission fragments shooting off the sail would provide thrust. It's estimated that a 10-kilogram payload pushed by this method could reach 250 astronomical units, way past Pluto, in just 10 years, using only 30 milligrams of antihydrogen. Then, there are beam core engines, which are maybe the most direct and potentially most powerful. These engines would try to directly use the charged particles, like pions, that are created during matter-antimatter annihilation. These high-energy particles would be funneled by powerful magnetic fields out of a nozzle, creating incredible thrust. Some designs predict these engines could be up to 64% efficient, possibly pushing spacecraft to a serious fraction of light speed. The implications are just staggering. An antimatter engine that could keep up an acceleration of 1 g could, in theory, get a spacecraft to Proxima Centauri in about 5 years of travel time. That's roughly 8,000 times faster than Voyager 1. Within our own solar system, travel times would be slashed. A trip from Earth to Pluto, which took the New Horizons probe 9.5 years, could potentially shrink to just 3.5 weeks. Exploring the entire solar system could take weeks instead of decades. There's even a company, Positron Dynamics, led by CEO Ryan Weed, that's actively developing an antimatter rocket engine based on positrons. They think their engine could be up to 1,000 times more efficient than current ion or plasma thrusters. Gerald Jackson, a former Fermilab physicist, has even suggested that with enough funding, we could be testing prototypes for antimatter-driven spacecraft within a decade, and operational antimatter rockets might be possible by 2050. Of course, the road to antimatter starships is full of huge challenges, mainly making and storing enough antimatter, like we talked about. But the sheer transformative power, the chance to turn sci-fi dreams of interstellar voyages into reality, makes it an irresistible goal for scientists and engineers. If we can crack these problems, antimatter could genuinely open up the galaxy for us. While starships heading to distant galaxies really grab the imagination, antimatter's revolutionary power isn't just for the cosmos. This same incredible energy source could also bring about huge changes right here on Earth, especially in medicine, and maybe even in how we power our world in the future. Let's start with medicine, where antimatter is actually already making a difference. The most common medical use of antimatter involves positrons, those anti-electrons, in a technique called positron emission tomography, or PET scans. In a PET scan, a patient gets a tiny amount of a radioactive substance that emits positrons. When these positrons bump into electrons in the body's tissues, they annihilate and produce gamma rays. Sensitive detectors then map where these gamma rays are coming from, creating detailed 3D images of what's happening metabolically inside the body. This tech is super important for finding cancer, studying brain activity, and diagnosing various neurological conditions. It lets doctors see how tissues and organs are actually working, not just what they look like, but PET scans are just the tip of the iceberg. Scientists are now looking into more direct and powerful medical uses for antimatter, particularly in fighting cancer. The antiproton cell experiment, AC, at CERN, studied using antiprotons for cancer therapy. Their research showed that antiprotons could be up to 4 times more effective at zapping tumor cells than protons, which are already used in some advanced radiotherapy. When antiprotons annihilate inside tissue, they release their energy in a very localized burst right at the tumor site. This precision could mean destroying cancer cells with much less damage to the healthy tissue around them, potentially leading to better treatments with fewer awful side effects. The idea of using antimatter particles, like antiprotons, to create super-focused beams for radiation therapy is a really exciting area of active research. Looking even further ahead, antimatter's unique properties could open doors to even more futuristic medical tools. Researchers imagine advanced diagnostic gadgets giving us unprecedented detail about the brain and nervous system. There's even talk of an antimatter scalpel that could theoretically make incisions at the molecular level, minimizing tissue damage and speeding up recovery from tricky surgeries. Antimatter particles might also be used in new drug delivery systems, guiding medicines with pinpoint accuracy to disease cells. While a lot of these ideas are still theoretical or in very early research, they're pretty tantalizing prospects. Now, what about energy for our planet? Since antimatter annihilation is the most efficient energy release known, with 100% mass-to-energy conversion, it's natural to wonder if it could be the ultimate energy source. As we said, a single gram of antimatter reacting with a gram of matter could release energy equal to several nuclear bombs. This energy could theoretically power entire cities or even countries. Unlike fossil fuels, it wouldn't create greenhouse gases. And unlike nuclear fission, some proposed antimatter reactions wouldn't necessarily produce long-lived radioactive waste, potentially offering a cleaner energy source. However, the practical problems with using antimatter for widespread energy are, right now, even more intimidating than for space travel or medicine. The main roadblocks are, you guessed it, the insane cost and incredibly slow pace of antimatter production, and the huge difficulty of storing it safely, and in large amounts. To power the world with antimatter, we'd need to make and manage it on an industrial scale that's currently way beyond our wildest dreams. The sheer amount of energy needed to create antimatter means that, with today's tech, we'd use vastly more energy making it than we'd ever get out of it. So it's not really an energy source yet, but more like an incredibly dense energy storage medium. Plus, the safety issues of handling large quantities of something so unbelievably energetic are serious, and accidental annihilation could be catastrophic. We'd need rock-solid containment and control technologies far beyond anything we have now. So, while antimatter power plants are firmly in the realm of distant science fiction for now, the theoretical benefits are too big to ignore completely. As research moves forward, and if we see some radical breakthroughs in production and storage, its potential as an energy source might one day become more realistic. For now, medical uses are the most immediate and real, with space propulsion being a tough but actively pursued goal for the medium term. The journey to harness antimatter is, without a doubt, exciting and full of incredible promise. But we have to be realistic about the colossal scientific and engineering mountains still in our way. These aren't just small technical details, they are fundamental problems that need clever solutions and maybe even some new physics. The biggest challenge, as we've mentioned, is production. Making antimatter is phenomenally inefficient and ridiculously expensive. Current methods at places like CERN produce only a tiny trickle of antiparticles nanograms per year, at a cost that makes it the most expensive stuff on Earth, estimated around $62.5 trillion per gram. To make antimatter a realistic fuel for starships or a common energy source, production efficiency would need to skyrocket by many, many times, and costs would need to plummet just as drastically. Scientists are always looking at new accelerator designs and techniques, but we really need a revolutionary breakthrough. Then there's storage. Antimatter goes bang instantly if it touches ordinary matter, so it has to be kept without touching anything. Magnetic and electric fields and penning traps can currently store small amounts of charged antiparticles like antiprotons and positrons for quite a while, even over a year for antiprotons in some experiments. But storing neutral antimatter, like antihydrogen atoms, is even trickier, often relying on subtle magnetic interactions. The current record for storing antihydrogen is only about 16 minutes. For any real-world use, especially for spacecraft on journeys that could last years, we need to be able to store much larger quantities, maybe kilograms, safely and stably for very long times. This means developing far more robust and possibly portable trapping technologies. One promising recent development is the Base Step project at CERN. In late 2024, they successfully transported protons, as a substitute for antiprotons, in a specially designed portable trap. This is a big step towards making antimatter research easier by allowing it to be moved to labs with better environments for super-precise measurements. The dream is to eventually have an anti-proton delivery service from CERN to other labs. And then there's the engineering of any device that would actually use antimatter. The annihilation process doesn't just release a lot of energy, it also blasts out intense radiation, including gamma rays. Any materials used in an antimatter engine or reactor would have to withstand these extreme conditions. Efficiently turning that raw annihilation energy into useful thrust or power, and safely dealing with the byproducts, are huge engineering puzzles. For propulsion, we need to figure out how to aim the annihilation products to create thrust without melting the engine or irradiating the spacecraft and everyone on board. The sheer energy density, while a huge plus, is also a safety risk. Controlling the release of this immense power is absolutely critical. Any uncontrolled release could be disastrous. Developing fail-safe mechanisms and procedures for handling even milligrams of antimatter would be essential before any practical application. Despite these daunting challenges, scientists around the world are not giving up. Research at CERN's anti-proton decelerator and ELENA facilities keeps pushing the limits, hitting milestones like the first trapping of antihydrogen, laser cooling of antihydrogen and positronium, and the first direct measurement of how antihydrogen behaves under gravity. These experiments aren't just about building engines, they're exploring the fundamental symmetries of the universe like CPT invariance and trying to figure out why there's so much more matter than antimatter in the cosmos. The Aegis collaboration at CERN, for example, managed the first laser cooling of positronium in 2024, a big step for precision studies. Innovations in cooling antiprotons to get them even colder are also paving the way for more precise measurements of antimatter's basic properties. The path forward means continued basic research, serious investment in new technologies, and breakthroughs in areas like particle accelerator efficiency, magnetic confinement, materials science, and radiation shielding. Developing transportable antimatter traps is a key future goal, with timelines for some of these advances stretching beyond 2040. It's a long road, but every discovery, every small improvement in making or storing it, takes us one step closer to potentially unlocking this extraordinary power. the journey into the world of antimatter is really just getting started, and there's so much more to explore. If you're fascinated by the absolute cutting edge of science and the incredible possibilities ahead, make sure to subscribe and hit that notification bell. What part of antimatter technology gets you most excited? Let us know in the comments below. We love hearing your thoughts and ideas. Antimatter. The word itself paints pictures of immense power, futuristic tech, and a deeper understanding of the universe. As we've seen, it's a substance that could completely redefine what's possible for humanity. From powering starships that could whisk us to the farthest corners of the galaxy, opening up brand new frontiers for exploration, to revolutionizing medicine with targeted cancer therapies and advanced diagnostic tools that could save countless lives. The challenges are enormous, almost as big as the potential rewards. The cost of making it, the difficulty of storing it, and the engineering headaches of safely using such concentrated energy are monumental. Yet throughout history, humans have always been driven by an unstoppable curiosity, a relentless urge to push the boundaries of what we know and what we can do. The quest for antimatter technology is a perfect example of this enduring spirit. Scientists at places like CERN and all around the globe are chipping away at these challenges. They're driven by the dream of unlocking not just new technologies, but also deeper insights into the fundamental laws of physics. Maybe even an answer to why our universe is made of matter at all. Every breakthrough, whether it's trapping antihydrogen for a few more seconds, cooling antiparticles to even lower temperatures, or taking the first steps towards transporting antimatter, brings us closer to a future that today might seem like pure science fiction. We are on the verge, not just of a technological revolution, but possibly of a new understanding of our place in the cosmos. The journey will be long and success isn't guaranteed. But if we can unlock the secrets of antimatter, if we can learn to wield its incredible power responsibly, the future it could bring is almost beyond imagining. A future where the stars are within our reach, and diseases once thought incurable become things of the past. The universe has given us a peek at its ultimate energy source. The rest is up to human ingenuity and our never-ending search for knowledge.